Alrighty, last one, our little mini series here on linear regression, linear modeling. We're going to talk about arithmetic sequences. So I did say that correctly. So when you're talking about like operations, like adding, subtracting, that is called arithmetic, but we say arithmetic sequences when we're talking about a type of sequence. So I am saying that correctly, promise. All right, so an arithmetic sequence is an ordered sequence, right? So the term order matters of numbers where the difference between any two consecutive terms is the same. So because these sequences are experiencing a common difference or a constant rate of change, they can be modeled with a linear function. Hence why we're talking about them in this chapter. Alrighty. So here is what's known as the explicit form, and I'm going to talk to you about what all these terms mean. That was kind of fun. So A sub n, so we say A sub n because it's a subscript. This is known as the nth term, but I'm going to specifically write that it means the value of the nth term. That way, sometimes I have students have problems differentiating between like the number term that it is and the number that's in that spot. So like third place, but like who is in third place, for example. A sub 1 here, that's going to be the value of 1, or you could say the first term. And notice that that subscript got replaced with number 1 because it tells you where that person is in the lineup. Like I'm A sub 1 in my family, right? I'm the first child. All right, next we have D, which stands for the common difference. This is whatever you're adding or subtracting by each time. And then n minus 1, n is the term number. So if I wanted to find the 394th spot in the sequence, I would just plug in 394 into this explicit form and it would pop out the value of that term, which is pretty cool. So this explicit form can sometimes be called the nth term form as well. All right, so typically arithmetic and geometric sequences have been taught just by what's going on in example 2, where you see a string of numbers and you have to figure out the pattern and write the equation. And even myself, a math geek, right, in school thought that was boring. So what I've done is I've given you one of those, right, so that we can say that we saw them. But I'm also going to give you a little bit of a story problem, right? It is technically a sequence, but we would probably just think of a linear model, like a boring old linear model for that. But my favorite way is the third example for each of these. We'll see a visual pattern. And I've noticed in my classes, students just really having a much better time with figuring out patterns if I give them some sort of visual, and you can see it growing or shrinking over time. So here we go. Corinne adds 4 books to her daughter's collection each month. So that adding 4 books to her daughter's collection right there, that is telling me my common difference. So that tells me that D, my common difference, is going to be 4. And you know what? I probably shouldn't have. Come on, scribble, erase. Okay. Probably should have used highlighter, right, for that because it looks prettier. So adding 4 books, that's our common difference. And she started with 10 books. So that is going to be our starting amount, or A sub 1. So we start with 10. So the explicit form for this would be a sub n, right? So I can plug in for n, the term number, however many months out I want. What if I want to know 300 months from now what's going on? Probably not 300 months, probably something like 24 months, right? 2 years later, what's going on? And it would be able to pop out how many books would be in her daughter's collection. All right, so according to this explicit form, the next thing is going to be my A sub 1, which is 10, right? There were 10 books to begin with. And then I'm adding to that 4 every month. And then from there, I multiply by n minus 1. Because that first month, right, we didn't multiply, or we didn't add 4, right? So that would, n minus 1 would become 0, so that would go away. And then every month after that, we're adding 4. All right. Next, this is the boring way we usually see this in explicit form to model this sequence. So again, I need to figure out a sub 1 and I need to figure out my common difference. So a sub 1 is fairly straightforward to come up with. It is just the value of that first term there. So let me know a sub 1 here is 5. I'm starting with 5. And then I need to think, how am I changing from 5 to 8, from 8 to 11, from 11 to 14? What's going on here? And I notice that I am adding 3 each time. So that makes my common difference 3. All right, so now let's write our form. A sub n is going to be equal to 5, my starting amount, plus 3, my common difference, times n minus 1. All right, and that explicit form is super nice because you can find any term number you want and you don't have to write out the whole thing. So, for example, I wouldn't, before, if I was just trying to continue on the sequence and I noticed it was growing by 3, I would have to write out, say, all 24 terms to be able to figure out the 25th term. But now I could just plug in 25 for n and find whatever that value is. Alrighty, here we go. The figures below depict a visual pattern that can be modeled by an arithmetic sequence. Write an explicit formula to model the sequence. All right, so what's going on? How many calculators do we have here? So we've got 1 calculator, then we got 6 calculators, then we have 11 calculators. All right, so I know that my A sub 1, we started with 1 calculator. And then from 1 to 6 and 6 to 11, I added 5 calculators each time to the image. So my D, my common difference, is 5. So that means my nth term form here, we're going to have A sub n is equal to 1, my starting amount, plus 5 times n is 1. And I can figure out how many calculators would be in, say, the 28th term. All right. More of the boring kind. So let's write an explicit formula to model this sequence here. So 50, notice 50 right away. 50, that's my starting amount. My A sub 1, my first term, is 50. And then I need to see how is this changing from term to term. So 50 goes to 47, which goes to 44, 41, 38. So we are taking away 3 every time. So totally fine that my common difference here is subtraction. So let's write our model. So I'll have A sub n equal to 50, then it'll be minus 3 times n minus 1. And now I'm asking you to find this value, A sub 8. So A sub 8 means I'm going to plug in 8 into my formula for n. So I'm putting the 8th spot in the formula. And normally what would happen is 8, that's not so bad. I probably could have written out all 7 terms that came before and then the 8th term and figure that out. But again, like I said, if I ask you for the 45th, the 57th term, as it gets gnarlier, you're going to be happy that you have that. So it's going to be 50 minus 3 times 7, or 50 minus 21, so 29. All right, so I am partial to the explicit form because, like I said, it's super handy for finding other terms in the sequence, but I'm going to show you another way that these can be written as well that I feel is outdated, but like I said, I'm going to show you anyways. So an arithmetic sequence can also be modeled by a recursive or by recursive forms. So with recursive forms, you'll have to know the previous term. That's why I don't love recursive models, because you have to know the previous term, right? So if you don't know it, then you're kind of like all poop. All right, so the recursive form looks like a sub n. Again, that's just the nth term. And it's going to be equal to a sub n minus 1, the previous term, plus d, your common difference. All right. So Aaron has been working to increase his bench press by 5 pounds per week. So increasing by 5 pounds, that's going to be my common difference. He's starting at 130 pounds. Okay, so 130 pounds is a sub 1. Okay. I want to write both explicit and recursive forms for this so that we can compare. So the explicit form, which is what we were just writing, looks like a sub n is equal to that 130 plus 5 times n minus 1. And now, like I said, I can figure out what Aaron's bench press would look like 13 weeks from now by just plugging that in. However, if you wanted to see what this looks like recursively, then you would have a sub n is equal to a sub n minus 1 plus 5. So whatever the previous term is, then you would just add 5 to it. All right, so now your recursive formula here for the boring sequence, we just need to find our common difference. So 3.5 to 4, okay, 4, 4.5, 4.5 to 5. Right, hopefully you can see that this is increasing by 0.5. So my recursive form will look like a sub n is equal to a sub n minus 1 plus 0.5. All right, and last but not least, we have a coffee pattern going on here. So the figures here depict a visual pattern modeled by an arithmetic sequence, right their recursive formula. So again, we need to see how many coffees we've got. 7, we got 5, and we have 3. So those are decreasing by 2 every time. So our recursive model would look like a sub n is equal to a sub n minus 1 minus 2. And there you go. Those are arithmetic sequences.